resume recording. Right. So the next one was to draw the diagram showing the power flow in the induction machine and briefly describe the components. So if I can find here, let's move this away here. It's like I'm picking up everything except the correct thing. This is the problem when you have too many screens. Right. So let's see. So we have the induction motor. So we're on the diagram showing the power flow of the induction motor. So we have, this is again straight from the notes, you have the input power. And then what happens? We have power going into the motor terminals, then it goes into the stator. So in the stator, you're going to have some losses with the windings. So you're going to have P copper losses in the stator, as well as you're going to have the core losses, right? So you're going to have losses in the stator and the core. This is just like a transformer, really. So you have those no load losses. And if you all remember, if you all think about the diagram or the equivalent circuit for the induction machine, you will see that it is just like the transformer, right? So just like the transformer, you have your core branch and your series branch, right? Your leakage parameters and so on. And here we have the air gap power. And this is the load, right? Which is really, this load is really the resistive equivalent to the mechanical load. So this represents the mechanical power, right? So we have the stator losses and the core losses. That is this one and this one. And after that, it goes through the air gap, right? So now here you have P air gap, right? So remember the construction of the motor. We have a stator on the outside cylinder, and then you have the rotor on the inside. So the separating these two things has to be a gap, otherwise the thing can't turn, right? You just have a transformer. So it goes through that air gap and now it gets into the rotor. And what happens when it gets into the rotor is that you're going to have some induction, you're going to have an EMF induced in the rotor, currents are going to start to flow in the rotor, and you're going to get some losses due to the resistance. So there you have PCU rotor, right? And after those losses, what you're left with is the power that goes to the mechanical system. That is this here. So you see, we took care of the stator, the core, the stator windings, the rotor windings, and what is left now is the mechanical power. And this is the total mechanical power that is converted from electrical power, right? So this represents all the mechanical power converted from electrical power. But all the mechanical power is not actually available to you as the user, right? Because the motor can't tell the difference between the load you put on it and the weight of the rotor itself. So the weight of the rotor itself, the friction and turning inside the machine and so on, all that is part of the mechanical load. So the motor can't distinguish these things. So you're going to have some losses here, which are what we call the rotational losses, or the friction and windage losses, right? So these things, we use them interchangeably, but essentially it means the power that goes into moving the mass of the rotor itself, right? And then after that, you end up with the output power, right? So this will be called the output power or the shaft power or the net power, anything like that, right? It is the power available to the user. And if you just remember this, and it coincides with your circuit diagram, well, up to this point at least, right? From here, both of these, the rotational power and the output power, are built into here, right? Into this total mechanical power. If you remember this, at least you should be able to figure out most of the questions pretty easily, because these things are all related, right? So this is what the next part is talking about in question 3. The question is to draw the equivalent circuit and show that the air gap power, that is the gross mechanical power, sorry, the air gap power, the gross mechanical power, the rotor copper losses, and this particular ratio. So if we draw the equivalent circuit here, as we did before, so this is our stator, and now we go into the rotor. Good. We have P, air gap. We have some current I. And what are these resistances? This resistance here is R2 prime. This one is R2 prime on S multiplied by 1 minus S. So now we want to find what are the powers. Well, power is simply I squared R. The same power goes through all of them. So the power crossing the air gap here is I squared multiplied by this resistance plus this resistance, which is R2 prime plus R2 prime on S multiplied by 1 minus S. The rotor copper losses is I squared. So this is PAG. This is P rotor copper losses, I squared R2 prime, and then P mechanical is equal to I squared R2 prime on S 1 minus S, right? So we could already see here, we just have to find the ratio of these things. So we could immediately see that we could simply get rid of these, right? Let's bring all of this to a single denominator. So this is S R2 prime plus 1 minus S R2 prime all over S. This is R2 prime, and this one is equal to R2 prime 1 minus S on S. Good. So I can now take out the R2 primes here, and this will give me 1 minus S. This is 1 over S. This one is equal to 1, and this one is equal to 1 minus S on S. Now I want the air gap power to be 1. So I multiply by S. So if I multiply by S, I should really not make these equals, right? Then this will become 1, this one will become S, and this one will become 1 minus S. And that is the ratio that we're looking for, right? So what does that tell us? That tells us that if you know the air gap power, you could immediately tell how these powers are being divided, right? The slip, remember the slip is the frequency, is the difference in frequency that from the stator, from the synchronous frequency of the stator to the rotor electrical and the rotor mechanical. So the power in the rotor electrical side, it goes into the copper losses, that is this. And the power that goes into the mechanical side is this, right? So this shows us essentially how this power is divided according to the slip. So the slip tells us that ratio that goes into the electrical, that stays in the electrical side, and the part that goes into the mechanical side, right? So, and of course, you can't reduce that to zero. You can't let all go to the mechanical side. If all goes to the mechanical side, it means the slip is zero, and then you're not going to have any induction happening, right? So you do need some sort of slip, right? So, right, so that is it for number 3. Any questions there? And if you all have questions, you could just type it in the chat. You could just jump in and ask it. You could unmute and ask it. So we can tackle them one time. Don't wait until things get too far and then you're feeling bad to ask the question. We could always go back. That's no problem. Okay, everybody all right? Okay. So now let's go to number 4. So number 4, we have a 400 volt, 3-phase, 4-pole, 60 hertz star connected induction motor running at 1728 RPM and 40 kilowatts. The stator copper and no load losses is 1 kilowatt. Rotational losses 1.6 kilowatts. Just 1 second. I have to take an important call here for 1 minute, and I will be back. All right. So I changed my phone, so I don't know who calling me anymore. So, right. So, good. Let me see, did I start back the recording? Yes, I did. I think yes. All right, nice. So let us go now to MATLAB. So we'll do it there. This is number 4 here, right? Good. Okay. So we have now we want to calculate the operating slip, the frequency of the rotor currents, the rotor copper losses, the efficiency of the motor, and the torque on the shaft, right? So we have all the given information stated out here: number of poles, pole pairs, which is number of poles on 2, synchronous frequency, RPM, input power, stator losses, which is the core losses plus the copper losses, and the rotational losses, right? So the first thing we want to do is find the slip. So we have the speed, the output speed, and we have the synchronous frequency. So based on those 2 things, we could work out the slip. So we work out first the synchronous frequency, which is F multiplied by 60, the frequency multiplied by 60 on the number of pole pairs, right? Notice this is a little bit different from what we did for DC motors. So DC motors, the pole pairs did not come into play at all, right? It was basically on just the just changing the speed from RPM to revolutions per second. And of course, for DC motors, we don't have frequency because it is DC, right? So here we have the 60 hertz, which energizes the stator, and that determines the rate at which the stator field rotates. We don't have that for DC, so the concept doesn't exist there, right? So we find the synchronous frequency, the synchronous rate of rotation, F multiplied by 60 on the pole pairs, and then we could quite easily calculate our slip by ns minus n on ns. Good. Rotor frequency, the rotor frequency is simply the slip multiplied by the frequency, right? So once we work out S, we just multiply it by 60 and we get 2.4 hertz. Next, we want to find the rotor copper losses, right? So rotor copper losses We know the rotor couple losses is S times P air gap, which is what we just figured out here in the section before, in the question before, right? So if we know the air gap power, we could figure out what the copper losses is quite easily because we have the slip. So how do we figure out the copper losses, right? So, well, actually, we're given the copper losses, P stator 1 kilowatt. So we simply take the input power, and this is why it's important to know these diagrams, right? So we know P air gap is P in minus the stator losses. So P air gap, P in minus P stator, so 40 kilowatts minus the 1 kilowatt, and then we multiply by the slip to give us the rotor copper losses. The next thing we need to find is the efficiency of the motor, and of course, efficiency is P out on P in, right? So we want to find what is P out. We already know what P in is. We were given P in as 40 kilowatts. So we need to find P out. So P out is simply P in minus the losses. So we were given the stator losses and the rotational losses. ROT is for rotational, not for rotor, right? So we had to find the rotor copper losses. So the output power is simply the input power minus the stator power. So we'll see that here in our diagram. See if I can reduce this a little bit. Right, so if we look at our diagram, we'll see there are three losses: the stator, the rotor copper, the stator losses, including the core, and the stator copper losses, the rotor copper losses, and the rotational losses. So those three things give you from input all the way to output, right? So here we have P in minus P stator, and P stator here takes care of the core and the copper losses, the rotor copper losses, and the rotational losses. So we minus those three things, we get P out, and then it is simply P out on P in. And then we want to get the torque on the shaft, right? So the torque is simply power divided by angular velocity. So we want here the mechanical speed, not the electrical speed. So it's not the synchronous speed we're using the mechanical speed, but we have to change it from RPM to what you call this thing, radians per second, right? So we change RPM to radians per second here. Why didn't we use the pole pairs? Anybody? Why didn't we use the pole pairs here? Who could tell me? Anyone want to take a guess? Nobody? Somebody take a guess? I'll give you all 5 seconds to type something in the chat. Anything, type anything that you think it could possibly be. One, two, three, 4, 5, nobody. Okay, so maybe I should start to call some people. Let me see. Eric Hunter. Ideas? Hello, Eric Hunter. All right. The question is why we were going here, we were calculating the mechanical speed. We were going from RPM to radians per second. So we're calculating here that, but we did not use the pole pairs. Here when we were calculating speed, we use the pole pairs. Why did we use it here and not here? Isn't pole pairs for synchronous speed? Well, yeah, that's sort of it. Sort of it. We get in there. Anybody else? So the pole pairs are when we're going from, right, so pole pairs are not necessary at the output, but the question is why? Why, when is it we would use the pole pairs and when would we not use the pole pairs? Right, so what we're looking at here is when we were finding the synchronous speed and using the pole pairs, the speed we were referring it to, right, to find the slip was a mechanical speed, but we had the electrical speed. So the pole pairs help us go from the mechanical to the electrical and vice versa, right? So the electrical speed is one thing, and the pole pairs translate that into the mechanical speed, right? So the electrical speed is from pole to pole, whereas the mechanical speed is actually physically on the rotor. So that is why when we were finding the slip, we had to work entirely in the mechanical side, or we could work entirely on the electrical side. Either way, we had one mechanical speed and one electrical frequency. We had to convert from one to the next. So we had to go, in this case, we went from electrical to mechanical, right? So we went from electrical to mechanical, so we use the pole pairs. Here at the output, we're not actually going from electrical to mechanical. We have the mechanical speed in RPM, and we just want to find out what is that in radians per second. So it is just a conversion of units. It is not converting from electrical to mechanical and back, right? Everybody clear on that? This is one of the tricky things that people often confuse. So they oftentimes in exams and so on, we would get people using these equations all over the place. So they would think, well, okay, you have to use the pole pairs for the induction machine and the synchronous machine. So they just use it everywhere they have an equation with speed. Sometimes they even use it for the DC motor, right? So this is the thing to remember about it. The pole pairs come into play when you convert from electrical to mechanical and back, right? That is what they allow us to do. Good. So we want P out on omega m. We have what the n is, so we could convert that to omega, right? Divide by 60 to get revolutions per second, and then we multiply by 2 pi because every revolution is 2 pi radians. And we divide it and we get 198.0595 Newton meters. Good. And this is the torque available to the user after the rotational losses are accounted for. All right, so let us go now to question 5. Everybody okay there? So you'll see the questions are actually pretty simple once you have the, once you understand how the power flows from one to the next, from one part to the next, right? Good. So now we have a 3-phase 440 volt star connected 4-pole 60 Hertz induction machine delivering an output shaft torque of 54 Newton meters at 1750 RPM. Mechanical losses in the shaft at this speed total 400 watts, right? So again, we have the mechanical losses that refers to the friction and windage losses or the rotational losses also. When the load is disconnected, the induction machine draws a current of 10 amps and power of 370 watts per phase. Resistance of the stator and rotor is 0.5 plus J0.5 per phase under standstill conditions. Then we have to determine all these things. So again, we can draw our diagram, right? So we have good. So we have 0.5 plus J0.5 and J 0.5 and 0.5 here. And then we have here 370 watts here. And we have P rotational at 400 watts. So we want, first of all, the slip at which the motor is operating, the mechanical output, the air gap power per phase, total input current per phase, and the efficiency at the given load. So we, again, just declare all our things. We have V line. Now, this is one important thing. We see in the question that it isn't stipulated whether it is line voltage or phase voltage. And when that is the case, it is a line voltage, which is the standard, right? So 440 volt star connected means 440 volt line to line voltage. So since you're working on a per phase diagram, we of course have to convert that to the phase equivalent, which means we divide it by the square root of 3. And we have still our 4 poles, so we get our pole pairs, our frequency. So here I calculated the synchronous frequency in radians per second. We have our mechanical speed, and then again our mechanical speed in radians per second. So you see there's already a difference there. Our torque, rotational losses, right. And then we have these things for when the load is disconnected. So of course that would be when the load is disconnected, it would be, right, when the load is disconnected, you would get the sort of no load power, right? So here we have right, so part A, calculate the slip. So we have NS, which we calculated above, by 60 on the pole pairs. Again, the same thing that we did before, and NS minus N on NS. So we could calculate the slip there quite easily at 0.0278. We want the mechanical output power, which is the shaft torque multiplied by omega M. This is just the opposite of what we did before when we wanted to find the we wanted to find the shaft torque in the last question. Now we have the shaft torque, which is 54 Newton meters, and we want to get the what you call it, the shaft power. So we just multiply by omega M. In this case, we already found omega M to be 183.2596. So we can calculate that pretty easily. We want to get the air gap power. So we know the air gap power is related to the total mechanical power, right? So as we saw in our diagram before, let me get this a little bit smaller still. Right, so we saw here in our diagram that the air gap power is related to the total mechanical power. And the total mechanical power is comprised of the output power plus the rotational losses. So here we have to get both of them. So Pmech is P out plus P rotational. Both of those we have. We just calculated the output power. We were given the rotational losses, right? So we calculate Pmech, and then we could simply use the slip to find what the air gap power is. So we know, again, from our ratios that we calculated, that they are related by 1 minus S. So we divide by 1 minus S, and we get the air gap power per phase here, right? Next, we want the total input current per phase. So again, based on our circuit diagram, we know the input power here is comprised of these two powers. So we could calculate what is the current coming through this branch, as well as the current coming through the no load branch. So the current coming through through this branch, we have the voltage, and we have all the resistances here, right? So we know that the resistance here is 0.5. We know the slip, so we could calculate the load resistance, because we know this is R2 on S by 1 minus S. And we know this is R2, so we just plug it in. We have the slip, and we can come out with the resistance value here. So we have the voltage across here now, which is 440 on root 3, and we have all of these impedances. So we could calculate V phase on the rotor impedance plus the stator impedance plus the load, right? So rotor impedance plus stator impedance plus load, and that gives us one value of current, right? And then we need to calculate down on this branch here. So we use the 370 watts and 10 amps, right? So 370 watts, 10 amps, this is when it is on no load. So we're just looking at this branch here. And we can get that from looking at P is equal to VI cosine theta, right? So P is equal to VI cos theta. We could work out what theta is. We know P is 370. We have the magnitude of the phase voltage, and we have the magnitude of the current. So we can work out theta, right? So this is, let's look at this branch, just this branch here that we're looking at. Right? So we have 440 on root 3, and we have magnitude of I no load is equal to 10. And then we have P, which is equal to VI cosine theta is equal to 370. We have this value, so we're just working out theta, right? So we work out theta, and that works out to be 1.4246 radians. And then we can find what the complex value of the current is, because we know that it is just the magnitude multiplied by cosine theta plus j sine theta, right? So we get that value there. So actually this should be minus j sine theta. Why we use minus j sine theta? Because it is an inductive load, so the current should be lagging, right? So, so we have the current here worked out, which was ISR according to our script. And then we have here I no load. So I in is simply the sum of both of them, right? And then lastly, we want the efficiency of the induction machine at a given load. So efficiency is P out on P in. We worked out P out before, so we need to work out what P in is. So P in is equal to 3 times V I cosine theta. This is V in I in, right? So this is at this point here. This is at this point here with this voltage and this current. Good. So we worked out what I in was. We have V in. We know what theta is here now. So we have 3 times V phase by I in magnitudes multiplied by cosine theta, which is the difference between the voltage angle and the current angle, right? So we work out P in, and then we just put P out on P in for the efficiency. Good? Any questions? No questions? Okay, so if no questions, let me show you all a bit of what we are going to do for the group project, right? So as I said, it's not finished yet. I'm just giving you an idea of where things are going. Hopefully by the end of this week, it will be done, and you will have to submit this really during the exam period or after. When we get your timetable, we will see what was a good time for you to do it, so you have enough time, right? So as you know, the university, usually you're not able to submit coursework during the exam period, but the university stipulated that if it is a coursework only course now, and this only happened this semester, that we could extend the deadlines into the examination period, right? So this is version A. There will be a few more like this. Probably, I didn't decide yet whether everybody will get the same thing, or everyone will get something different, or maybe a few different things. So you're working at a robotics company, and you're going to design a terrestrial rover for autonomous data collection in the Arizona desert. And you have some criteria to meet from the design team, and you have to specify some motors for the application. So you're given some things. You're given the vehicle mass, the max speed, the max acceleration, or wheel size, wheel type, ground type, maximum slope. And you have to basically spec out 3 motors: a permanent magnet DC motor, an induction motor, and a permanent magnet synchronous motor to be considered by the design team to meet these things, right? So you're going to do a technical report, and you're going to look at calculation of the shaft torque and power, considering the specifics of the application. So you'll have to look at these things and figure out what the requirements for the application would be. And then you'll have to develop some curves, torque, power, and efficiency with speed for the motors. And you'll have to do some simulation. So you should be familiar with already with the motors in Simulink. So you would know that in Simulink, you could basically go on in the motor block. You could choose a motor from a set of predefined motors. So you'll be choosing one of those motors. You don't have to, I don't expect you all to go and figure out what the parameters of the motor should be. So it is just to pick one of the motors, an appropriately sized motor from the library, and then you're going to analyze performance. You're going to run some simulations, see how the motor behaves starting when it's going up to peak speed, and then if it's operating and you have some change in the load torque, look at that and see how see what happens with the with it and discuss the results and so on. So this is similar to what you would have to do in practice, right? So, and you might be from 2 and 3 and so on, you should be okay because you should have been doing this already. But number 1, that will be a little bit different. It will take some independent study, but it's not difficult. It's some basic physics that you have to look at, right? So you should know some of the physics already from A-levels. It's very basic physics. And you'll have to look at things like coefficient of friction and so on. So this is where the rubber, the hard dirt, and so on will come up. If you look for coefficient of friction and how to calculate torques and so on, there are a lot of tutorials and these sorts of things online, and they'll give you coefficient of friction for different surfaces and different wheel types and that sort of thing. So this will help you to determine what is the torque requirement for the motor. Good. How you all feel about that? Right. Okay. Nice. And we're actually doing a lot of this sort of work now. I'll show if I can find the. I want to dig up in that now. Anyway, so right now we're actually doing a number of projects where basically this is, yeah, just these 4 things. But don't think it's just 4 things, remember? So each motor you're doing these things, right? So this will hopefully serve as a template for you if you want to do this sort of design in the future. When you start to do these types of projects, you'll realize there are all sorts of issues, practical issues that you never thought about before when doing it. When we're doing like some projects now in designing robots for transmission lines and for sanitization spaces and so on, and just to get the wheel fitted to a shaft is a problem, and you come across problems like people specifying some things in metric and some things in imperial units. So the difference is if somebody says like a 12mm shaft, right, which is in metric units, the equivalent to that people will say is a ½ inch. ½ inch is really 12.5mm. So what do you think is going to happen when you try to fit the shaft in the wheel, right? It's just a hair too big, right? So these are the sort of practical issues you come up with, or things like gearing. If you have one motor and you want to use it for a different application, what are the types of gears you could use, right? So these are some of the practical things that you could look at that you'll have to deal with when you're doing projects out in the real world that we traditionally don't really cover in the program because they're more practical issues. They're more, well, it's not that we don't do practical issues in the program, but I mean, there's not things that require a lot of theoretical knowledge, and computation is something that you could pick up on the go, but there are things that are nice to know going into it, right? So this is where you could explore all of those things and see, well, how if you have one particular motor, and you have the freedom to do this in the project. If you have one particular motor that has the power requirement, but it doesn't have the torque requirement, you could say, okay, we're going to do a torque transformation on this using a gear, right? So, and a gear is essentially like a transformer for mechanical power. So just like in our electrical transformers, we have one power and then we transform the voltage and current. Gears, you have one power and you transform the torque and speed. So you could, if you have an application and the only way the torque is being met is with a very high power motor that might be too big, you could use gears or so to increase the torque and reduce the speed of a smaller motor that might have the power requirements. So these are things you could look at in the project in your motor selection, and you could say, okay, this motor does not meet the spec, but we're going to gear it down using a particular gear ratio, right? And all these are things you can pick up pretty quickly with some independent study, right? The groups have not been released yet. That will be maybe by the end of this week or next week again. And yes, it is a group project. There'll be 3 or 4 people in a group. So you'll see there are 3 mottos that we're dealing with. So each person could deal with one, and everybody together could look at the specking of the motto as well as the discussion of the findings, right? And when it is released, which will be end of this week, start of next week, you will have to sometime in the examination period to do it. So as I said, we will look at your exam schedule and so on, make sure it's not it doesn't come up when you have a lot of exams due. So we'll find a nice date and put it for them. All right. Okay. So that is it. Any questions?